Welcome to another video from Lockdown Electronics with me, Bill. Now you may recall a few weeks ago I did a review on the Gochifix multimeter with a oscilloscope built in, and at the end of that video I said I would do another video where I actually tried to use it in a practical sense to see if I could learn a bit about electronics. So I've set myself a challenge, and the challenge is with a breadboard and a few components and just the Gochifix meter, can I actually explore some circuits? So that's the challenge I'm going to attempt. So we'll go straight to the bench and have a look. Okay, so a while back I said I would use, when I did the review of this Gochifix meter, I said I would make another video and see if you could do anything useful with it. So that's what the plan is today. So first of all, I'm going to switch on and I'm going to go up to continuity and diode mode. I'm going to select diode there because I've got a silicon diode here, and if we just check the forward voltage for that, yeah, about 6.1 volts, something like that. Yeah, 0.61 volts. So what I'm now going to do is explore AC and DC waveforms and the act of rectifying things. So I'm going to go now back to volts, and I'm going to do a long press on the middle, and I'm going to go into the signal generator. I'm going to select a sine wave, and we're at 3 volts peak to peak, which is good, and the output is on. So now I'm going to do a long press to go into oscilloscope mode, and just to check I've actually got that, here is this orange wire is the output of the signal generator. So let's just pop the lead onto there, and we'll do an auto, and there we are. We've got our sine wave. It's at 1 kilohertz, and it's saying 2.92 volts peak to peak. And if you look carefully at the display, you can hopefully it's 1 volt per division, so we have got 1.5 there plus 1.5, so 3 volts peak to peak. So it does agree. So first thing I want to do for a bit of an experiment is let's just rectify that. Don't worry about the other components for a moment. So if I just put the signal generator output and then put it in series with a diode, like so. Now we get that waveform, which looks a bit weird because but we're in AC coupling here. So let's go to DC coupling. So it's an odd shaped sine wave, but you can see there's a lot more of it above the line than below. So that seems perhaps outwardly a bit strange. Actually, it isn't a bit strange. This is a phenomenon that you're probably familiar with already. Have a quick look at this screen grab. This is from my Siglent oscilloscope, and this is what the Siglent makes of that same setup. And that's because currently we've got the output of the generator through a diode, but it's not loaded in any way. So now what I'm going to do is this jumper here, if I connect this jumper to the negative rail on the breadboard, that'll put a 3.3k resistor here in series, if you like, with it, so it gives us a load. So if I pop back to where I was before, we've got that rather strange waveform, and I'll now connect the ground, so that's now in circuit, and straight away you can now see probably what you might expect, which is half wave rectification. So the diode is allowing the positive going waveform through, but not the negative. And again, here's a grab from the Siglent, and you can see the scope does indeed agree with the Siglent. Now, because of the forward voltage of this diode, we haven't actually got 1.5 volts high pulse here. We've got, well, it's saying round about a volt, something like that, and we checked before the forward bias voltage, and as you can see, if you take that off the 1.5 volts, you end up with what you've got there, which is roughly 1 volt. So first thing we've discovered here is, with a little setup, is that yes, you can rectify something, but without a load on, you get a bit of a strange reading. So let's just now take that a step or two further. So here I've got a 2.2 microfarad capacitor, and currently the positive side is connected to the output of the rectifier, but the negative side is not connected. So if we ground that should put a smoothing capacitor in across our power supply, and that should give us something that looks a bit more like DC. So I'll do that now. And yep, there you go. You can hopefully see that reasonably well. We've now got DC, and it's actually saying on the measurement here we've got about 780 millivolts average voltage coming out, something like that. So that would make sense, because that's the forward bias voltage of the diode and minus the half-wave rectification. So yeah, it's something like. So yeah, we've explored power supplies there, and we've also begun to understand how a power supply's output, certainly an unstabilized one, how a power supply's output can fluctuate if it's not in some way under load. And a lot of those what they used to call wall wart transformer power supplies, that are basically a small transformer that plugs into the wall socket. Most of them these days are switch mode, but the wall wart ones, they had a transformer in, some still do, and when it's not under load, you find it puts out quite a bit of a higher voltage, which perhaps does look a bit of alarming when you measure it, but once it's actually working, the voltage is different. So okay, there we go. That's allowed us to investigate half wave rectification and smoothing, but we've only got 0.8 volt, so it'd be nice to maybe look at full wave rectification, but if we try and do that, we're going to end up with almost no voltage at all on the output to play with. So what else could we do? What else we could do is a bit of transforming. So I'm going to get set up with a transformer, and then we'll have a look at the kind of thing we can do with that. Okay, here we are back, and this time the only real change is we've now got a transformer here. So I've got the output from the SIGGEN feeding into one side of the transformer, and I've got the output of the transformer going to the same diode, same capacitor and same resistor as before. So let's just have a look what's going on now. I've been using 1 kilohertz, and this is not a power transformer, it's actually an audio output transformer, but it's what I had to hand just to do a bit of demonstrating. So I'm just using 1/2 from the center tap to one side on the primary here, and on the secondary here, or whichever way around you want to say it, there's just 2 connections. So I've got the AC signal 1.5 volts. If we just disconnect that, and it does indeed show up there as the 3 volts peak to peak. Now because it's going to be under load going into the transformer, I won't quite get 3 volts peak to peak. Let's just see what we've got there. So we've got, according to the measurements here, just over 2 volts peak to peak now across the primary. So let's have a look at the output of the secondary, and using the same scale you can see straight away that we've got a step up going on. So we've exchanged the AC waveform is the same, but we've stepped it up, so there'll be less current now, but the voltage is greater. And currently that's saying currently that's saying just under 14 volts. So we're stepping up from that side, which is about 2 volts, up to about 14 volts, and there won't be a lot of current, and we'll soon be getting rid of that in the rest of the circuit. But that's the action of a step-up transformer, and doing this at 1 kilohertz is a bit better for this kind of transformer. It's an audio output transformer, so it's the kind of frequency it was designed to work at. So on the input side of the diode, we've still got that AC waveform. If we now go to the output side of the diode, you can see we are getting half wave rectification just there. Yeah, and if I now put the smoothing capacitor into circuit, it's charged up, and that's saying we're getting about 6 volts DC available as an output. Now currently I've not got the load connected up, so it's unloaded, and what I wanted to show here was that classic thing that happens with unstabilized power supplies. Their output voltage is a lot higher when there's no load condition. So I've got the same resistor I was using before for a load, just a nominal amount, so I'll now connect that across the output, and straight away you can see we drop down and we're actually now getting about 1.9 volts, just under. So in reality we haven't got a great deal more out of it, but what we have been able to see here is we've been able to see the action of stepping up through a transformer, the action of the smoothing capacitor. If I take the smoothing capacitor out of circuit and leave the load on, you can see there that what the smoothing capacitor is actually doing, it's taking the top bit of the waveform and it's allowing it back into the circuit, and that's where the smoothing action comes from. So the capacitor is attempting to top up each trough, if you like. Now I don't propose to do this now because you've probably had enough, but the other way to do this would be to use a bridge rectifier, where you'd rectify both halves of the waveform and then you can add them together, which would allow you to produce a greater voltage actually, because they wouldn't have quite so many troughs to fill in. It wouldn't be smooth, but there wouldn't be that whole half cycle of trough to fill in. So there we go. So that's the Gochifix using the signal generator and the scope, and you also saw me using one of the meter functions earlier, which was the to check the diode. So yeah, if this is all you've got and a few components and a breadboard, you can do electronics. I'm not even got a power supply here. Everything is happening just with the meter. I'd have been thrilled to bits with that when I was a lad. So yeah, you know, appreciate not everybody's got loads of money to throw at this. So with something like this, you can actually start to see what's going on inside circuits, and I think that's a really powerful way to learn. Okay, having reviewed the footage of those 2 sections, I sort of realised that there's a bit of unfinished business, so we really need to go back and have a look at a full wave rectifier. So let's hop back to the bench and do that. Okay, so similar arrangement, but now we've got instead of a single diode, we've now got 4 arranged in the pattern of a bridge rectifier. I'll just put a graphic up showing you that circuit diagram, but it's fairly straightforward and probably well known. So I've still got the same 3 volt peak to peak going into one side of the transformer, got the stepped up output coming out on those 2 yellow jumpers, fed to the input sides of the bridge rectifier, which is there and there, and then I've got one side of the rectifier grounded here because I've got a common ground on the scope, and then the output of the rectifier is here. Now at the moment it's not connected to anything. I've got the capacitor and load resistor, but they're currently not connected. So let's have a look at the output, and surprise surprise, you can see an odd shaped waveform when you'd probably expect to see full wave rectification, and that's simply because it's not under load. So let's put that load resistor in circuit. Incidentally, yesterday I referred to it as, I think I referred to it as 3.3k. It is of course 33k, 3 orange bands, apologies for that. So let's put it in circuit, and instantly we've now got a very different looking shape, and I'm going to just increase the height of that so you can see it a little better. But we've definitely got full wave rectification going on there, and if I just make it look a little bit easier to see. So we've now got both halves of the waveform, if you like, now appearing on the top. So if we now pop in our smoothing capacitor, we should get a higher voltage. So let's just see what we actually get. And that's now settled down, and it's saying 1.86 volts, and it's higher because of course it's got a more reliable input. Remember, when we were doing half wave rectification, we only had every other waveform to work with, but now of course we've got every cycle. So in fact we've got every half cycle, I should say. So we've got a higher output voltage. So there you go, that's full wave rectification. Okay, well I think I met the challenge. Managed to explore some circuits just using the Gochifix with nothing else, no power supply or anything, just a few components on a breadboard. Very simple. And if you're new to electronics and learning about stuff, there's quite a lot there which you can start to get your mind going and thinking through how things work. When you get strange readings on the scope, there's possibly reasons for it, and we've been able to explore that today. So I think that was the challenge easily met. So I hope you've enjoyed it. Thanks very much for watching, and hopefully look forward to seeing you on the next video.